Okay, let's start. Now we'll start a new topic, optimization. Okay, so we'll talk about optimization. The whole idea here is that there's a story. Okay, so we start with the story. Okay, so here we start with the story and ask what is the best way to do something. Okay, so it's a paragraph long story. Okay, so you read this, you understand this, then you translate this into a calculus problem. Okay, here you solve the problem. Solve this calculus problem. Okay, so what happens is you generally find something like x equals 5. Okay, so what is the best way to do something? The answer x equals 5 is obviously not compatible with each other. Then you translate this back, translate this result, this solution, to a human answer. Okay, so here you write the best way to do something is to take, etc., etc. Okay? So what we are interested is, or what everybody is interested is this part. Here is our story. What's the best way to do it? And here is the answer. The best way to do it is to take the following steps. Okay? So what goes in between is your responsibility. The person who is asking this is not interested whether you are taking derivatives or integrals. Okay, so that's your professional ability here. But the actual human interaction is this part. Okay, so that's what we will do in the first few hours. We will look at problems like this. We'll translate them to calculus, solve the calculus problem. Most of the time, the calculus problem will be easy for us because the problem is cooked up in that way. Okay, so let's start with a simple example. Okay. Okay, so let's say you have, let me put the numbers, 1,200 meter fencing. Okay. You want to face, you want to cover a rectangular region. You want to fence of a rectangular region, rectangular orchard, let's say, along a river bank. Okay, so how should you do it so that you get the largest orchard? Okay. So this is the problem. Now we translate it to calculus. In our case, okay, so in our problem, we have this part is the river. So this is the river bank here. And you want to construct, this is your orchard. Okay, and you give dimensions to this. The width is x, and this part is minus 2x, right? So the sum of these things should be 1200. Okay, and you want the area depending on x is a of x, and you write a formula for a of x. Okay, so it is x times this, x times 1200 minus 2x. Okay, you are not finished here because you realize that this is a polynomial. It is defined for all values of x, but our problem doesn't make sense for all problems of x. So here x can be 0. Okay, so you don't get any garden, but at least x can be 0. Okay, and x can be 600, right? Okay, so if x is 0, then you get a thinner and thinner and thinner garden, and eventually you just put this fencing from here to here. Okay, so you cover that part of the bank, but you don't get any garden. And in the other case, you and back for 600 meters. Again, you don't get a garden, but at least the problem makes sense. Okay, so if x is larger than 600, the function makes sense, but the function now does not address our problem. Okay, so the problem is this. We have this function. Okay, so this is our function. Okay, so this function models our problem. Okay, so the problem is to get the maximum area, so we want to maximize this. So the problem above translates to finding the maximum of this, the max value of this function on the given interval. Okay, so we know that in calculus now it's a totally calculus problem, a simple problem. We have a function on an interval, on a closed and bounded interval. We want to find its maximum. So you look at the endpoints. You look at the points where the derivative does not exist. In this case, it's a problem. The polynomial, its derivative always exists. So that is out. And then you take the derivative and find the roots of the derivative. Okay, so since the endpoints are easy, let's leave it to the second stage. Then we find, okay, so we consider a prime x equals 0. Okay, so here a of x, let's do this. A of x is equal to 1200x minus 2x squared. So a prime x is 1200 minus 4x. I want this to be equal to 0, and this gives me x equals 300. Okay? So now calculus tells us that evaluate a of x at this point, and at this point. Okay, so let me write the numbers here. Okay? And then consider these numbers. A of 0, which is 0. A of 300, which I calculated to be 1800,000. And A of, the last thing is 600, so that's again 0. Okay, so from here we conclude that the maximum of A occurs at x equals 300. Okay, so now we have to give the answer to this. Okay, so find an answer. Okay, so answer. The largest orchard will be obtained when its dimensions are so what did I say? 600 meter or 600 meter length and 300 meter width. Okay, so this part is going to be 300 meter and this part is going to be 600 meter. Okay, so this part is of course changes from person to person. Okay, so you can word this in any nice way you like. But this maximum number of course will not change. You can of course parameterize this in a different way. You can call this part x and then this part you call something else. And then of course you will have a slightly different function whose maximum will occur at some other point. So you see x equals 300 is not essential for this problem. What's essential is the dimensions, these dimensions. Okay, so if you choose this as your x, apparently x would be 600 at the critical point. Okay, so this is one of the simplest problems. But this has a historical background, a problem which is still considered as okay. So historical background for this thing. This is the problem. So this is a historical problem. Suppose you want to find the maximum area of a region, or rather of the region whose boundary is fixed. Okay, so you are given, I don't know, one 500 meter rope, and you are asked to cover a region with this 500 meter rope, and it's yours. Okay, so historically that was the that was the situation. Okay, and they solved it as a circle because intuitively that's the best thing that comes to mind. Okay, but to this day it's almost an open problem because you see, this is when you say this, especially in the old times, you are talking about nice regions with nice boundary. With today's sophistication, not every region has a boundary. Okay, the boundary may not be so-called rectifiable, so you have to add some conditions. Depending on your conditions, you have very complicated problems. But in calculus, we can solve this as follows. So check Wikipedia for this thing. I forgot the name. This is about Carthage or something. Okay, so a modified form which can be solved by calculus. Okay, so such problems are within the domain of what is called calculus of variations. But now this can be solved by calculus. Here we restrict this to be a semicircle. Okay, so here we have a semicircle whose center is somewhere here. So its center can be anywhere. Find the largest sector such that the length of the arc is fixed. Okay, so we remove a lot of problems from this statement, a lot of indeterminate or parts which require definition. Here we define the region. The region will be this circular region, this sector, and we want this length from here to here, which is now well defined, to be a fixed number. So where should you place, what should be the dimensions of this circular arc? So actually here you are trying to call this your x. And of course you have to find this direction, okay? So here you want to find the largest radius, and you want to find the best radius and best position for the center so that this area will be larger. You can solve this in calculus, but it's a little bit long, so I won't do it in class or maybe some other time. Okay, so let's continue. Of course, this one is a modified version of this. This is totally trivialized. Okay, so you are just multiplying two numbers. There is no other thing moving. Okay, so let's look at another problem. Now, most of the other problems we'll have will be geometrical problems, so that we don't have indeterminacies like this. So what do we mean by a region? What if the region doesn't have a boundary but has an area? Okay, so these are technical questions. So, okay, so the next problem we will talk about is this one. So this is again a typical optimization problem. A cylindrical can is to be made to hold, let's say, according to the problem, 1 liter liquid. Okay. Find the dimensions which will give the minimum surface area. Okay, so sometimes this is in fact real life, because you want to construct a cylindrical can to hold something, and of course the cost of the can mostly depends on the surface area. You are using some material there, so you want to minimize it. Okay, so in real life this is a little bit more complicated, because top and bottom material of the can has to be a little bit different than the size. If you look at the tomato paste cans, you see that they are a little bit different. So that will add a little bit more complication to this. And of course, if you are not selling tomato can, if you are selling something for pleasure, then the shape of the can is another factor. Okay, so sometimes you have to consider that if the shape is going to sell this can, who cares about its dimensions? Okay, so you can just add it to the cost, to the price. So for example, cola bottles are not designed according to this, they are designed according to pleasure. Okay, so you look at the can and you want to hold it. Okay, then they charge you for all the cost of the bottle. Okay, so going back to our problem, so we want to find the can with the minimum dimensions, the minimum surface area. If we didn't have this, okay, so the can with minimum surface area is the zero can. Okay, if you don't have any can, then it doesn't have any cost. Okay, but we have a restraint here. Okay, it has to hold a certain amount of liquid. Okay, then you realize that that's something good, not a restraint, because the volume depends on two parameters: the height of the can and the radius of the top and bottom. So far, we don't know how to solve minima maxima problems with two variables. We will learn this next semester. But this condition now relates those two parameters to each other. So we can write one of them in terms of the other, and then we put it here in the formula for the surface area. Then we get a formula for the total surface area of one variable. Then we take its derivative, equate to 0, and then start thinking. Okay? So let's do it as we did here. Okay, so here we are talking about a can like this. Okay, so this part is height, this part is radius. Okay, so volume is equal to pi r square h. Okay, base area times height. We want this to be equal to 1. But then these things will be 0 point something, etc. So we make this 1,000. So this is 1,000 cubic centimeters. Okay. So from here we can solve one in terms of the other. Normally the temptation is to take the simplest one. If I choose this one and express it in terms of h, I'll have square roots. But if you are doing this with a computer, who cares? You can do it. But if you are going to take derivatives by yourself, then you want to avoid square roots if possible. So here we say h is equal to 1,000 over pi r square. Surface area. So let's say which I used a of x. Okay, surface area is, okay, so let me, before giving a name to this, let us write the surface area. So I have two of these bottoms, 2 pi r square plus the perimeter here times height, 2 pi r times h. Okay, so that's the surface area. Now I replace h. I replace this h with this number here. So we have a function. We have a function. A depends on r. Okay, here I have r. Here I replace this and I have r. A of r. So 2 pi r square plus. Okay, let me write this 2 pi r, and h is 1,000 divided by pi r square. Okay, so after our function, calculus function to minimize is a of r equals 2 pi r square plus, after you cancel this, this is 2,000 over r. Okay, what is the domain of r? R can be as small as we like, okay? But here algebra doesn't allow us to say r equals 0. Well, in practice, r equals 0 means we just give up and don't construct anything, and the boss gives the job to someone else. Okay, so that in order to stay in the job, we take r positive. Then we can take r large as we like. In return, h will be smaller. Okay, so there is no upper limit for r. Okay, in real life, of course, if you want to take a very large r and you take 1 millimeter h here, so nobody wants to construct that can, but theoretically that's possible. Okay, so we leave it there because it makes sense. So in this setup, you want to minimize this function. Okay, so before doing anything, we just take the derivative, equate that to 0, solve for r, and after that we start thinking about what we will do with those numbers. Okay, so a prime r is equal to 4 pi r minus 2,000 over r square. Okay, so you equate this to 0. This is 4 pi r cubed minus 500 divided by r square. I want this to be equal to 0. So r cubed is equal to r cubed is equal to 500 over pi. R cubed is cube root of that. 500 over pi, 1 over 3. So this is approximately just to have some idea about what we are talking about. This is 5 centimeters. Okay, so this is going to be 5 centimeters. This length is, the diameter is 10 approximately. Okay. Now we'll evaluate A at this point and also at the end points, but there are no end points here. The end points, in the sense that the end points of the interval are open. So in those cases, you take the limit when you approach to the boundary. Okay, so we calculate. Okay, so let me make a note of this. So first, let me calculate A at this point. See if I did that. Oh, I didn't calculate this. Okay, so we calculate limit r goes to 0 from the right of A of r. Okay, that's infinite, right? This is infinite. And we calculate limit r goes to infinity, A of r. Okay, so this is our interval. So if you draw the picture of the interval, it is like this. You start from here, and then all these numbers are allowed. This is our interval. When you approach to this one, the surface area increases beyond bound. If you go in this direction, then this part makes the limit infinite. Okay, so we have only one point, one critical point. Actually, one point where the derivative vanishes. Okay, only one point where A prime r equals 0. So that point must give the minimum. Okay. And I warn you that next semester, this is not true for functions of two variables. If you have a function of two variables, so on the plane, the plane is your domain. On top of that, you have a surface. And of course, the local minimum and local maximums will be points where the tangent plane is parallel to the xy plane. Okay? But not every such thing. And if you have only one point where the tangent plane is parallel to the xy plane, and it's the point where the derivatives vanish, one is tempted to say that it is a local mean or maximum. Again, go to internet and find interesting examples. Because if you have several variables, the functions behave very creatively. But in one variable, we have a graph. Okay? So it says that the graph is something like this. Okay? So it comes from infinity, and then it goes to infinity. And we have only one point where the derivative is 0. Okay, so that point must be the minimum. Okay, so before we give the answer, we have to calculate h also. Calculate also h at that point. Okay, so here I think I calculated h. So h is equal to, calculate this, and you'll find this is 2r. Okay, you just put it there, simplify, and you notice that it is 2 times this number. Okay, so now we give our answer to this. So, answer. The most, well, these are my words now. You can word it in any way you like. You can explain it in detail. You don't explain the solution, okay? You just explain the shape of the best can, Okay, so my answer is something like this. The most economical can, which will hold 1 liter, should have base radius. Okay, so I'll write this and let the boss figure out what that is. Approximately 5.4 centimeter and height twice that. Okay, so you see now it makes sense. Okay, I have a question here. I'm saying find the dimensions which will make this surface area minimum, the cost minimum, which will minimize the cost. Okay, so the question is inverse, and the answer is that such a nice box, cylindrical can, will have these dimensions. Okay, so nobody cares about your taking limits, the interval being open, etc. Okay, so that's your responsibility. Okay, so any questions so far? Okay, let's do another thing like this. So find the maximum volume for a right circular cone inscribed in a sphere of radius r. Okay, so this is not an everyday problem. Okay, so but again, you realize that our solution, if we solve the problem and find x equals 5, that's not going to be an answer, because when you draw the figure, there are several ways of taking something as the parameter. Okay, and according to that parameter, you'll find a critical point for the function. Okay, so nobody knows what function you are using, so saying that for your function takes a critical value at a such and such point doesn't answer the question. You use your critical point, etc., find the volume in terms of r, and you say the maximum volume possible for a right circular cone inscribed in a sphere of radius r is, and you write the volume. Okay, so that should be the answer. Okay, let's see how we approach such a problem. Okay, so we have a three-dimensional figure, a sphere, and inside that we have a cone. So we cut it along a plane passing through the origin and North Pole and South Pole, from the tip of the cone and through the center of the sphere, and we will get a two-dimensional picture which describes this setup. Okay, so this is the plane and this is the North Pole. We choose the North Pole as the tip of the cone. And the cone is something like this. Okay, so in my case it looked like an equilateral triangle, but it's not. So center of the cone is center of the sphere is here. So this height is r. Okay, so this distance is r, and in my solution here, for some reason I chose this as x. Okay, and this part is length. This part is L. Okay, so my parameter will be x. You can choose this whole thing as h, and you can call it as your parameter. Obviously, that also describes to you what's happening. Okay, so if you call this h, then h can be 0, you don't have a cone. H can be large, and when h is here, again, you don't have a cone. So your parameter h will be between 0 and 2r. In my case, the parameter can be negative. So if the cone is here, okay, I'm now moving backwards here. Okay, so since I call this as a distance, I'm going in this direction. So if if the base of the cone is here, in my setup, x will be negative. So the range of x in this setup is from -r to +r. Okay, so you can choose other things. If you are masochistic, you can choose L as your parameter. Okay, so equations will be a little bit more complicated, but that also totally describes the situation. Then your L, your parameter will be between 0 and L. Okay, so it will be maximum here. If you go up or down, it will be small, and eventually it will be 0. Okay, so this is my setup. Volume of this cone is, well, cones are 1/3. Base area pi r square, where here r is L, pi L square, times height. Height is, in my case, x plus r. Okay, so this is my volume. Now I have the two parameters here, x and L, but obviously they are related. I have to choose one of them. Well, I choose x as my parameter, so L square will be easy. Okay, so L square is equal to r square minus x square. Okay, so that makes life easier. Okay, I put it in here. Hence, the volume of such a cone is V, depending on x in my formula, 1/3 pi L square is r square minus x square times x plus r. Okay, now I go back to my discussion here. X is between -r and +r. Okay, so this is the function to minimize and maximize, but we know from the geometric description that the minimum is 0. In fact, we check after you write a formula like this, you should check, because it's obvious here. If x is -r, then the cone is just this point, the volume is 0. So you put x equals -r, this factor makes it 0. Also this factor makes it 0, so that's okay. When x is r, we are here, and we just have this line as our degenerate cone, which has volume 0. So you put x equals r, here it is 0. Okay, so far so good. This doesn't tell us that we are doing something correct, but at least we are not doing something embarrassingly wrong. Okay, so this is the function to minimize, maximize in this case, because the minimum is 0. Now we take the derivative. Since it's a calculus problem, after you write the problem, you take the derivative. In fact, in most calculus exams, if you take the derivative of every function you see in the question correctly and don't do anything, you should generally get a passing grade. Okay, so that's how easy calculus is. Well, check what's going on. Okay, so that's generally what happens. So you see a function, this is calculus, you take its derivative and see what happens. Okay, so I take its derivative. Before taking derivative, I expanded this and made it a polynomial in x so that it is easier to take the derivative, so that when I take the derivative, I got this. R square minus 2rx minus 3x square. Then, if you have a derivative in calculus, you equate that to 0, and you find the roots are as okay, so x is equal to minus r, or x is equal to r/3. Okay, so that's what you get by solving this quadratic equation. Okay, so this is an endpoint, so I will consider it later. So this is my critical point. Okay. I look at the function. Okay, now I start thinking here. Okay. I look at the function. In this range, the function is always positive because x will never exceed r. So the function is always positive. At the end points, I just calculated before starting that at the end points, the function is 0. So in between, the function is always positive. It will have a meaningful maximum. There is only one critical point in between. So that is the global maximum. Okay? So we calculate these things now. V of minus r equals 0. V of r over 3. Let me see where I calculated this. This is 32 pi r cubed over 81. And V of r is again 0. Okay, so this is again as we are required to do in calculus. You find the critical points, you evaluate the function at the critical point and at the end point. This end point turns out to be also a critical point, but we don't care. That's not important for us. Okay. So again, look at this function. This function makes sense for all values of x. Okay, but we don't want that. And what do we want now? Okay, so I think that's all. Now we can answer the question. But at this point, you may wonder the ratio of this to the sphere. You should also check that this volume is smaller than the volume of the sphere. If you find here a number which is larger than the volume of the sphere, then you don't show this to anyone. You go back and check where you put a minus instead of a plus or vice versa. Okay? So in calculations, you also check those things. Well, I keep telling you today how to check these things because this month I had an article in Bilim Teknik, and there I multiplied 3 by 25, and I write 100 there. So the issue sold 20,000 copies. Now people are staring at this. What does it mean? So you have to check those things. Okay, so I think that's all here. Now we can answer this question. So the question will be in terms of this. So the maximum volume for a right cylindrical cone, well, not cylindrical cone, circular cone, right circular cone inscribed in a sphere of radius r is 32 pi over 81 r cubed. Okay, so this turns out to be approximately 30% of the volume of the sphere. To be precise, 8 over 27%. Okay.